4.3 is on monotonic functions and the first derivative test. So I have a picture here. Sketch this out. I want to talk about this thing. So just suppose this is some polynomial. It goes like this. You can see that it goes down like this to the left, goes up to the right. And when we're looking at a function and we talk about a function increasing or decreasing, or the overall concept is monotonic, meaning it doesn't change direction, we always think left to right. Okay, so we always go left to right like that. So left to right. So way over here, so you don't think of it as you're going this direction. You're always starting towards negative infinity out there, and then as you approach this direction, what's happening to the function? That's how we interpret the functions and just define them. It doesn't really matter, but that's just how we look at it. So as this function goes left to right, ignore this arrow here, it's always this direction. So it's way down here and then it's coming up. We would think of this as increasing. The function is getting larger. It's increasing all the way to b, right there. And then after b, you can see the function is going down. We're going to call that decreasing, right? It makes sense. It's intuitive. And then at c, it changes again and goes to increasing, like this. So the picture is pretty clear what's going on. Then we have to define it mathematically, of course. So we're going to say this. So this function we can see is increasing from negative infinity all the way to b. So we want to have a way to describe it. So what we do is we pick two values, x1, x2, or whatever you want to call it, inside that interval. And then we want to see that in this case, f of x1 will be less than f of x2. And then you can see that means it's increasing. So that's how we'll do it. We're going to pick two values and use an inequality to define it. Okay, so that's what the picture represents. So let's look at the definition. So this is the definition of increasing and decreasing. All right, so on let's see. So a function, seeing how I want to start it, a function is called increasing on an interval I. So right, so just pick some interval from a to b, like that. So it's increasing on I if x1 less than x2, so that's what my picture looks like above, implies, so increasing, that means what? We want this value to be less than this value. Then that means it's increasing. That implies f of x1 is less than f of x2. And that's true for all x1 and x2 in the interval I. So we're actually, the interval could be from negative infinity, but we can just say, let's just pick a to b. From a to b, the function is increasing. Okay, and then similarly, a function is called decreasing on an interval I. And let's just pick this interval that actually works up there above, b to c. And this is still the same, x1 less than x2. So you're still doing x1 is less than x2. You're still doing that. implies, and then how would you change that? That implies f of x1, and then you're flipping it around, right? This value here is greater than this value here. So you say f of x1 is greater than f of x2. And that's true for all x1, x2 in the interval. All right, so if it's always increasing or always decreasing, we call that monotonic. Okay, so that's where the monotonic comes from. So monotonically increasing and decreasing means it's always doing that. All right, so that's the definition. Hopefully you've seen that before somewhere. Let's look at a theorem of how to test that. This is where the derivative comes in. So this theorem is the test for monotonic functions. All right. So f is we're going to assume f is continuous on an interval. So suppose f is continuous on an interval I, a to b, and differentiable on the open interval from a to b. Sound familiar, right? And that's how we often define things with with mean value theorem, Rolle's theorem. That's kind of how it often goes. Okay, then we have two cases. A, if f prime of x is greater than 0, so positive, for all x in the open interval from a to b, then f is increasing and I like to use this arrow like that because writing out increasing takes forever, is increasing on AB, the interval on I. And then B, similarly, if f prime of x is less than 0 for all x on AB, then f is decreasing. And I'll just use the arrow down like this on AB. So that's what you'll be able to do, is just take the derivative and see if it's true on that interval, and then we'll figure out when it changes from increasing to decreasing. That's kind of what we're after. So we can see if you have a function. I'll erase these later, but if you go, this means it's increasing, right? Slope is positive, and then you change to decreasing. Well, that's what we want to look for. We're going to look from increasing to decreasing, and that'll be the first derivative test. We'll get to that later. I'm getting ahead of myself here. Okay, so let's look at the proof of that. So let's prove that. Why is that true, right? I mean, what does that mean? Okay, so here's the proof. And we'll do A. So we need f to be continuous. So assume f is continuous on the closed interval from A to B and differentiable on the open interval from A to B. All right, so now we need x1, x2 in the interval. So now we're making this assumption right here that it's in the interval. So we're going to let x1 and x2 be in AB. And actually, it doesn't really matter if it's in the open or closed, but we're going to just be in the closed is fine. And we're assuming x1 is less than x2. All right, so then if f is differentiable on the open and continuous on the closed, you automatically get the mean value theorem. So we can basically just say that. So by the mean value theorem, we have that form. So by the mean value theorem, what does it say? It says there exists a C in the open interval from A to B such that, and I'm going to write this a little differently, but you can verify, you get f of x2 minus f of x1 is equal to f prime of C times x2 minus x1. When I showed it to you, I basically just said f prime of C is equal to the change in y over the change in x. So I put this in a denominator. So that's all the only difference. Okay, so then what we're going to show or say is the assumption here, or the implication here, is saying if f prime is positive, then f is increasing on AB. Okay, so we're going to make that assumption that it's positive and see if we actually get this implication. Okay, so that's what we're automatically saying that. So let's see. We're just going to assert that now because that's what we are trying to see. F prime of C is greater than 0. We also have x2 minus x1 is greater than 0 by assumption, right? Because of this. Both of those imply, so that implies that this has to be greater than 0, that f of x2 minus f of x1 is greater than 0. So I'm just saying that's greater than 0 because that's what we're saying it is. This has to be greater than 0 because that's by assumption. x1 is less than x2. Then, because of the equality, this has to, they're equal, so this has to be greater than 0. Okay, if that's true, then that's equivalent to saying f of x2 is greater than f of x1. Or just flipping that around, f of x1 is less than f of x2. And that's, by definition, it implies it's increasing. And that's pretty much it. Therefore, by definition, you don't have to say that part, f is increasing on AB. Okay, so B is the same argument. So that is something you have to prove. And here's our first example of how that mean value theorem can come into play to prove a theorem. So I want you to look at this. I want you to study this. It's kind of subtle, but it should make sense. It should make sense of all the pieces put together with those inequalities. Okay. Now let's look at an example. Basically showing something's increasing or decreasing. Okay, so find first example is find where f is increasing or decreasing. So, like the intervals, I didn't put out all the little details there, but find the intervals, right? So f of x is x cubed minus 2x squared plus x. So basically what you do is you find out where f prime is equal to 0, because that is where it changes from increasing to decreasing, or vice versa, from decreasing to increasing. So that's the first thing you can do, is just start taking derivatives. F prime is 3x squared minus 4x plus 1. You set that equal to 0 and solve. Okay, so you factor it, product of two binomials. It's going to be 3x, and then it's got to be minus 1 and plus 1. And then x, or I'm sorry, two minuses, minus, minus. And then the sum, of course, is the negative 4. So you get two values where it changes sign. So f prime changes sign at 1/3 or at 1. So f prime will change sign. And that's what we're looking for, right? I mean, basically, because of this theorem, f prime is increasing if it's positive, and it's decreasing if it's negative. So right at 0, it's not doing either. So that's what we're looking for. This will lead to the first derivative test. Okay, so it's where it changes sign. So then you can set up a chart or something. I'll show you kind of both. So what I'll do next is set up a little bit of a chart. So this is the interval. And then we'll look at f prime of x and then f of x. So it'll look like this. So the point is, really, you just need to be organized of what's going on here. So this interval would be from negative infinity up to 1/3. Okay, and I didn't show a test value, but let's put one in here. And then like what you're going to test. So the test value is kind of what you're going to plug into the interval in here to see what it is. So between negative infinity 1/3, 0 is probably the best test value. So you want to see what f of 0 is. And you don't always have to evaluate it, but if you do, it's fine. You just look at it and see what's going on. The next interval, excuse me, is between 1/3 and 1. So in that interval, you can test maybe a half. So you do f prime of a half, and you can verify all these. It's less than 0. So the key is this is positive, this is negative. And then we're going to test from 1, and then we're going to approach infinity. And so you probably test, I like to test like large values, like 10, but often you can just test what's, the next integer or something. F prime of 2 is greater than 0. So it's a positive. So what does that imply? That implies it's increasing, and then it's decreasing, and then it's increasing. So it's increasing on those intervals. So this is increasing on this interval, decreasing on this interval, and then increasing on this interval. Okay, so that's what it's telling us. Now, just because I really can't help myself, let's graph this thing. So let's take a look at f of x cubed, because this is actually very doable to graph from college algebra and stuff, plus x. You can see that 0 is a intercept, so you can factor out x. You get x squared plus 2x plus 1, and you can see that easily factors. That's a perfect square trinomial. That is x. I should have put as a minus in there, huh? Need to keep that minus. So that's x minus 1 quantity squared. So there's a double root right there. So your roots are x equals 0, multiplicity 1, so it passes through. I won't get into that so much right now, but if you did college algebra, you would have seen stuff like that. So it passes through 0, bounces off 1, and then it goes through it. The y-intercept is 0 as well. So this is the x and y-intercept always when it happens like that. Okay, and so when you are evaluating this thing, or let's graph it. So when you graph it, we know because this is positive and that's odd, it goes up on this side and down on this side. So it's going to go through 0, 0, 0, and then go through or bounce off 1. So it goes up, and then at 1/3, it changes sign. So it's decreasing all the way to 1/3. And so 1/3 is up here somewhere, and then it goes and just touches. So it basically goes like this. It comes up, passes through, bounces off, and goes like that. Okay, so you can see it's increasing to 1/3, decreasing to 1, and then increasing after. Okay, so let's graph that thing. Let me blow this up a little bit to graph it. So it comes up like this, and then takes off after that. How does that look? Don't really like the way I drew it the first time, so we'll just fix it. And we'll go in and erase when we need to, places we need to erase. Have to take your time on these things. It just has to look decent. We can put those lines back in, no problem. Anybody graph digitally? Draw digitally? I never could like that. I don't draw very well anyway, but I never really liked the digital drawing stuff. All right. So there's a root right here, and then here's 1. This is a third. Pretend it's a third, and this is basically f of 1/3. All right, so we'll talk about that as a max and min shortly, like soon. Like this is this is a local max, this is a local min, and we'll talk about stuff like that. All right, we have plenty to do here. We're going to break this up a little bit. So let's go ahead and pause, and we'll talk about the first derivative test and then do a number of examples on that.